Good day, the topic is buoyancy. Let us consider a fully submerged cylinder to determine the net hydrostatic force. First, for the net hydrostatic force along X, consider the projected surface. Assign hydrostatic forces F sub Hx1 and F sub Hx2. For the net horizontal force along X, Fh net at X is equal to F sub Hx1 minus F sub Hx2. But same unit weight, H bar, and area A, thus the value of F sub Hx1 is equal to F sub Hx2. Therefore, Fh net along X is equal to 0. Next, for the net hydrostatic force along Z, consider the projected surface. Assign hydrostatic forces F sub Hz1 and F sub Hz2. For the net horizontal force along Z, Fh net at Z is equal to F sub Hz1 minus F sub Hz2. But again, same unit weight, H bar, and area A. Thus, for our Fhz1 is equal to Fhz2. Therefore, the value of Fh net along Z is equal to 0. It only means that the value of the net horizontal force at any orientation is equal to 0, since the hydrostatic force towards the surface at one side is equal with opposite direction at the other side. Next, for the net vertical force, this is along Y. Assign hydrostatic forces, we have F sub V1 and F sub V2. V1 for the downward, that is the force at the top of the cylinder, while V2 is for the force that is below the cylinder. So for the net vertical force, we have FV net equal to FV2 minus FV1. But same unit weight, gamma. So for our FV1, so it is equal to the gamma times the volume above the curve. While for FV2, it is equal to the gamma times the imaginary volume of fluid above the curve. Updating the equation and simplify, for us to assess further, let us identify VI, or the imaginary volume, and V. So for volume, the imaginary volume above the curve below, or below the cylinder, minus the volume above the cylinder is equal to the volume of the submerged object. Updating the equation of FV net, it is therefore equal to the gamma times the volume of the object, or otherwise that is V sub O, or others use that as V sub B, or the displaced volume. And this is the equation of the buoyant force, or BF. That is again equal to gamma of the fluid multiplied to the volume of the submerged object, or the displaced volume. So buoyant force is always acting at the center of gravity of the submerged volume. Therefore, for Archimedes' principle, a body immersed in a fluid is subjected to an effective upward force, or the buoyant force, that is equal to the weight of the fluid displaced. And when a body is immersed in a liquid, we have three different cases. First case, floating body. It rises to the surface of the fluid and floats when the density of the body is less than the density of the fluid. Second case, the suspended body or that is neutrally buoyant. So the body remains at rest at any point in the fluid when its density is equal to the density of the fluid. And for the last case, third case, that is the sinking body, the body sinks to the bottom when its density is greater than the density of the fluid. So an example is if you opt to swim, some floats while others sinks because the buoyant force is dependent on the volume of your body. So the bigger the volume, higher chance that you will float due to higher value of buoyant force. So let us now take our sample problems. So for problem number 1, a block of wood of 0.2 meter thick is floating in sea water. The specific gravity of wood is 0.7, while that of the seawater is 1.03. Find the minimum area of the block which will support a man weighing 100 kilograms. So for our solution, consider the FBD of the system by assigning corresponding concentrated loads. W of the man, weight of the wood, and buoyant force of seawater due to submersion of the block. Then apply some forces vertical equal to 0, upward equal to downward forces. Upward force is the buoyant force of seawater, while downward forces are weight of the wood and weight of the man. For buoyant force, BF, so we have BF SW is equal to the gamma of the seawater multiplied with the volume displaced, that is the volume of the block. But for the gamma of seawater, it is equal to the product of specific gravity of seawater and unit weight of reference fluid, that is water. And for volume, that is the product of the minimum area or A-min and uniform thickness of the block. Substitute specific gravity of seawater as 1.03, gamma of water as 9.81 kilonewtons per cubic meter, and the thickness of the wood as 0.2 meter. The updated value for BFSW is 2.021 times A-min in kilonewtons per square meter. On the other hand, for weight of the wood or W sub wood, it is equal to the gamma of wood times volume of the wood. But for gamma of wood, it is equal to the product of the specific gravity of the wood and unit weight of reference fluid, that is water. And for volume, the product of the minimum area or A-min and uniform thickness of the block. Substitute S of wood as 0.7, gamma of water as 9.81 kilonewtons per cubic meter, and thickness of the wood as 0.2 meter. The updated value is 1.373 times A minimum in kilonewtons per square meter. And for the weight of the man, or W sub man, it is equal to the mass of the man times the gravitational acceleration. So substitute the weight or the mass of the man as 100 kilograms and the gravitational pull as 9.81 meters per square second. Thus, for the weight of the man, it is equal to 981 newtons, or that is 0.981 kilonewtons for us to be consistent. So for the updated equation, transpose the value of the weight of the wood at the left side of the equation. Extract A-min and cross-multiply 2.021 minus 1.373 kilonewtons per square meter. Cancel units and simplify. The value of the minimum area is 1.515 square meter. Lower than this value, the block and man will sink. but higher than this value, it will still float because it will consider a higher buoyant force for the wooden block. For our sample problem number 2, a piece of wood floats in water with 6 centimeters projecting above the water surface. When same wood placed in glycerin with specific gravity 1.35, the wood floats with 8.5 centimeters projecting above the glycerin surface. So determine, first, height of the wood, second, specific gravity of the wood, and last, the weight of the wood if the cross-sectional area is 20 centimeters by 20 centimeters. Again, we are dealing with same piece of wood but different fluid samples. So consider first the FBD of the two cases and assign the weight of the wood and buoyant forces. We have BFW for water and G for glycerin. First requirement, determine the height of the wood or H sub wood. Consider case 1 and some forces vertical equal to 0. Thus, BFW is equal to the weight of the wood. On the other hand, if we will consider for case number 2 and same some forces vertical equal to 0, the value of the buoyant force for glycerin is equal to the weight of the wood. Since the weight of the wood is the same, we can now equate the two equations. Thus, BFW is equal to BFG. For BFW, it is gamma of water times the displaced or submerged volume for case number 1. For BFG, it is gamma of glycerin times displaced or submerged volume for case number 2. Update the equations for gamma of glycerin and volume. Cancel common terms for both sides, such as gamma of water and A of wood, and substitute specific gravity of glycerin as 1.35. Then distribute the value of this specific gravity and rearrange the equation unknowns at the left. Therefore, the height of the wood is 15.643 centimeters. That is for requirement letter A. Next, consider specific gravity of the wood, that is S wood. You may consider equation either from case 1 or case 2. For this sample, let us consider case 1 equation, wherein BFW is equal to W of the wood. For the buoyant force of the wood, it is equal to the gamma, buoyant force of water rather, it is equal to the gamma of water times the displaced or submerged volume for case 1. And the weight of the wood is gamma of the wood times the volume of the wood. Update equations for unit weight and volume and cancel gamma of water and A of wood and cross multiply the value of H wood and substitute H wood as 15.643 centimeters. Therefore, the specific gravity of wood is 0.616, lighter than the two fluids since specific gravity of water is 1 and specific gravity of glycerin as 1.35. That's why the sample wood floats. And for the last requirement, the weight of the wood if the area of the base is 20 centimeters by 20 centimeters. The weight of the wood is equal to the gamma of the wood times volume of the wood. And gamma of the wood is equal to the specific gravity of the wood times the gamma of reference fluid, and the volume of the wood is A of the wood that is of its base 20 centimeters by 20 centimeters and multiply to the predetermined height of the wood. Substitute S of wood as 0.616, gamma of water, the reference fluid, as 9.81 kilonewtons per cubic meter, area as 0.2 by 0.2 in meter, and height of wood as 0.156 meter. The weight of the wood is 0.038 kilonewtons. Then let us consider the application of buoyancy, the statical stability of floating bodies, and with condition that any floating body is subjected to two parallel forces, the weight and the buoyant force. For the analysis, consider the floating body either at its upright position, either small or no tilting action, or when body tilts due to air or wave action for the stability analysis. So it is our goal to check if the tilting object can be pushed back by weight and buoyant force to its original position, or these two forces will help the body to overturn or otherwise fail. An example of this is a ship or a boat. For it to be stable, it must withstand the impact of waves and air and maintain its center of gravity at its balance condition. So let us now consider the elements of a floating body. First is the weight of the floating body, W, with downward direction and always acting at the center of mass or gravity of the object. Next is the buoyant force or BF, always upward and equal to the weight of the floating body. It is acting at the center of buoyancy of the displaced or submerged volume. Next is G, the center of gravity. Then B sub O, the center of buoyancy for upright position. And we have BO prime for the center of buoyancy for tilted position. Next is M, the metacenter, the point of intersection between the line of action of the buoyant force and the axis of the body. Next is the angle theta, or the angle of tilting, measured at either the immersed or immersed portion from initial to final maximum tilt of the body. On the other hand, for our measured distances, for MBO bar, it is the distance from metacenter to the center of buoyancy. Next is for GBO bar. It is the distance from center of gravity to center of buoyancy. And finally, we have the distance mg bar. It is the metacentric height, the determinant of stability, and that is the distance from M to G. For the computation part, consider the metacentric height. For mg, it is equal to MBO bar plus or minus GBO bar. Use plus or positive or addition if G is above BO, and minus or subtraction if G is below BO. Next, let us determine values of MBO bar. First, for initial MBO bar, for small or approaching to zero value of the tilting angle, theta, MBO bar is equal to I all over V sub D. Otherwise, some used as V sub O, the volume of the submerged object, where I is the moment of inertia of the section of the body along free liquid surface. Comparing transverse and longitudinal, it is more critical in terms of rotation along the transverse section. Thus, an example for the moment of inertia, such as rectangular plane, it is equal to I, that is equal to 1 all over 12, times B times H raised to 3. Applying to the equivalent rectangular plane for section at free liquid surface line, I is equal to 1 all over 12 times, consider the side parallel to neutral axis, the axis of rotation. So that is the length L, times the side that is perpendicular to the neutral axis, which is the width W. Then this be raised to 3. And for V sub D, so it is the volume displaced or submerged. On the other hand, for MBO bar, this is intended for greater value of angle of tilt or angle of theta. MBO bar is equal to small v times small s all over V sub D times sine of theta, where V or small v is equal to the volume of the wedge of immersion or immersion. Choose only one. Anyway, most likely the immersion and the immersion volume are equal. Immersed portion is the portion originally exposed to the atmosphere, then submerged due to tilting of the body, while immersed portion is the portion originally submerged, but due to tilting, it is exposed to the atmosphere. And for distance S is the horizontal distance between the center of gravity of the wedges. Again, our wedges are the immersed and the immersed portion. So for this S, it is often 2/3 of the width, W or B, along the transverse section. So for V sub D, so it is often the same as the V sub D for the initial MBO, since V for immersion is often equal to the V for immersion. For the couple and identification if it is stable or unstable, assume that it will tilt clockwise. First condition, it is stable if M is above G. Why? Because analyzing the sample, tilting rotation, such as clockwise for this example, the couple due to equal forces, the weight and buoyant force, creates a counter rotation. Thus, W and buoyant force pushes back the block to its original orientation. For this condition, couple moment is righting or resisting moment, represented with Rm, equal to W times X, or the buoyant force times X. Second condition is it is unstable if M is below G. Why? Because analyzing the sample, tilting rotation, clockwise for this example, the couple due to equal forces, weight and buoyant force, creates same rotation. Thus, W and BF further pushes the block to overturn and fail. For this condition, the couple moment is overturning moment, or OM, equal to W times X, or BF times X. So let's apply in our sample problem. So for the problem, a rectangular scow, 30 feet wide, 50 feet long, and 12 feet high, has a drop in seawater of 8 feet. For this drop, this is the portion which is submerged. So its center of gravity is 9 feet above the bottom of the scow. For letter A, determine the initial metacentric height. For B, if the scow lists until one side is just on the point of submergence, determine the righting couple or overturning couple. Use specific gravity of 64 pounds per cubic foot. Again, this is sea water unit weight. For the first requirement, that is the initial mg or mg bar, assign location of M and BO. So that is at the center of the submerged part of the body. For mg bar is equal to MBO bar plus or minus GBO bar. Again, let us assume that M is above G. For initial MBO bar is equal to I all over V sub D, where I is equal to 1 all over 12 times L times W raised to 3, since the critical section is along the transverse. And for the volume displaced, it is L times W times the draft height D. Substitute L as 50 feet, W as 30 feet, and draft D as 8 feet. MBO bar is 9.375 feet. For GBO bar, based on the diagram, G from the base is 9 feet. Then for BO, from the base, it is half the draft, that is 8 feet. Therefore, GBO bar is 5 feet. For this case, indeed correct assumption that M is above G by inspecting MBO bar and GBO bar values. Thus, consider the system under stable condition. And since G is above BO, we will adopt minus or subtraction process. Substitute MBO bar and GBO bar values. Therefore, MG bar or the initial MG bar is equal to 4.375 feet. For the second requirement, if the scow lists until one side is just on the point of submergence, what is RM, righting or resisting moment, or OM, that is overturning moment? So for letter B. First, for MG bar is equal to MBO bar plus or minus GBO bar. Based on assumed orientation of the body, M is above G. Next, determine MBO bar. That is equal to VS over VD sine of theta, where the volume of the wedge is 1/2 times the base of that triangular side, 15 feet, and times the height, that is equal to the total height, that is 12, minus the draft height, which is 8. So it is equal to 4 feet. Then it will be multiplied to the length of the scow, that is 50 feet. Next is for S. For S, use 2/3 of the width, that is 30 feet. And for the volume displaced or submerged, it is the same volume as the initial condition. That is 50 times 30, then multiply to the height of the draft, that is 8 feet. Then lastly, for theta, so we will consider the tilting process or tilting condition. Thus, for theta, use the arctan or the inverse tangent of the opposite, which is 4 feet, all over the adjacent side, that is 15 feet. Therefore, for MBO bar, it is equal to 9.703 feet. And for GBO bar, same as the initial case, it is equal to 5 feet. By assessment of GBO bar and MBO bar, indeed M is higher than G. Thus, it is still stable. then G is above BO. Therefore, in equation, use subtraction sign or difference of the two. Substitute values. The distance mg bar is 4.703 feet. For the unknown, since it is stable, therefore determine the writing or the resisting moment Rm. For Rm, you may use either W times X or BF times X. But since values of W and BF are unknown, it is easier to solve for the value of BF. Thus, we will use the equation Rm is equal to BF of seawater times the moment arm X. For the buoyant force of the seawater, it is equal to the gamma of seawater times the submerged volume. Substitute gamma of seawater as 64 pounds per cubic foot, while for the volume submerged, same as the initial, that is the length 50 feet times the width 30 feet and multiply with the draft height that is 8 feet. Therefore, the buoyant force of the seawater is 768,000 pounds. On the other hand, the moment arm or the lever arm X, consider the right triangle representing the distance mg, X, and tilting angle theta. By trigo function, the sine of theta is equal to the opposite, that is X, all over the hypotenuse side, which is the distance mg bar. Rearrange, X is equal to mg bar times sine of theta. And substitute values, we have mg bar, 4.703 feet. Then sine of theta, again, optimize the value of the theta by using the tilting position, that is for theta, the arctan of theta is equal to the opposite side of the triangle, that is 4 feet, all over the adjacent side, that is 15 feet. X therefore is equal to 1.212 feet. For the writing moment, substitute the values. The resisting or writing moment is 930,575.422 pounds feet. Or some use the unit, that is feet pounds. Again, for this problem, since M is above G, it is stable. Thus, the requirement is writing or resisting moment. Okay, so that's it for the discussion of buoyancy. Take care and God bless.